Let's solve the parachutist problem using the numerical approach. You can see here that we will employ a step size of 2 seconds for the calculation, and our mass and drag coefficient are given. So if you remember, our velocity at the time of e plus 1 was equal to vti, plus we had the slope function, which is g minus c over m, vti, and ti plus 1 minus ti. This final term is the step size, so we can just say that this is 2, meaning that we will increase the time with increments of 2. And the initial velocity will be 0. Here we can write it down as ti, not ti, but the t1 is 0. If we start with I equals 1, t1 is 0, and v1 is 0. v1 and if we type down the noun values, g is 9.18. Let me write it down here instead of g. 918. And for c and m, let's write down 12.5 and 68.1. So here, now we will start with I equals 1. Then let's say this way, if I equals 1, t is 0, t1 is 0, then v1 is 0 as well. These are the initial conditions. And with I equals 2, we will start, but actually with I equals 1, we will start finding the second velocity. Then t2 equals, I'm going to use this equation now. Here vti is v1, so 0 plus 9.18 minus 12.5 divided by 68.1. vti is again vt1, which is 0 times 0 times 2. So here, if we calculate, we will see that we obtain only 9.18 times 2, which gives us vt2 as 19 over 62 meter per second. If we continue calculating like this, let's increase I to 2, and t2 is 2, we are increasing by 2, and v2, we already found v2 as 19.62. Now we can calculate vt3, which is equivalent to 19.62 plus 9.18 minus 12.5 divided by 68.1 times vti is now vt2, which is 19.62, and the step size is again 2. And this is equivalent to 32.04 meter per second. So if we continue, if I equals 2, vt4, I will quickly complete them all. vt4 is 32 sorry, let's write this way. If I equals 2, 3, T3 is 3, V3 is 32.04 meter per second, I equals 4, T4 is T3 was 4, T4 is 6, V4 is 39.9 if we use the same numerical equation, meter per second. I will not write down the details anymore. If I equals 5, T5 is 8, V5 44.87 meter per second, I equals 6, T6 is 30, T6 is 10, and V6 is 48.02 meter per second, I equals 7, T7 is 12, V7 50.01 meter per second. Finally, I will say so we can continue this up to infinity, and at the infinity time is infinite, and infinite is 53.44. We already mentioned about this in the analytical solution, and with these results we can again plot the time and velocity graph for this numerical approach as well, and in the end we can find the comparison between the analytical and numerical solution. In this slide, we are comparing the numerical and analytical results for the Parachutist problem. As you can see on the left-hand side, we have analytical results that we calculated before, as well as the numerical results we calculated in the previous slide. And you can see that there is a difference. For example, at second 2, the analytical is 16, about 16, and the numerical is about 19. And we can see that this difference exists for all values. But when we increase the results, the actual differences are getting closer. And if we draw this on a graph, as you can see over here, the gray one is the exact solution, which is the results of these. And the approximate solution, these are drawn over here. So you can see that the approximate solution is kind of a linear approximation, because our Euler method, which has the slope and the time step size, has only linear approximation for this curved graph. And because of the linearity, we can see that there is a difference as well as the shape difference, but still we can capture the overall trend of the analytical solution. And here, if we reduce its step size, by the way, because we have only increase of 2, the increases are large. If we reduce the step size to 1, for example, we will have a better approximation of the analytical solution. Still, the numerical is linear, but decreasing the step size will increase the predictive performance. So this is an important part that we need to think about for this problem. Not only for this problem, for all numerical approaches actually, the increasing the step size will increase the approximation accuracy. However, this will come with a computational cost, because we need to calculate all the values for each step size for each of the times that we need to use. That's why for the numerical approaches in general, we can get closer to the exact solution by decreasing the step size or using more data. but this will increase the computational cost. And actually, with the use of computers, this computational cost is not a problem anymore. If we use hand calculations, it's a problem because we need to calculate them all by hand. But by computers, it's easy to calculate these using, for example, MATLAB. And we will show using MATLAB for this example in later chapters. And we will see that we can approach to the exact solution in a better way.